Hold 2 bags of sugar, one in each hand, a meter apart. There is a force between them. It is real, it has never once switched off, and it is pulling those 2 objects toward each other right now. Its strength is roughly the weight of a few dozen blood cells. That force is gravity, the first thing you ever learned about physics, and the one you are most certain is finished. But here is what they left out. Nobody knows how strong it is. Newton wrote his law without the number in it. The first person to measure that number worked alone in a garden shed in 1798, and in the 2 centuries since, as the instruments improved beyond anything he could have pictured, the answers did not converge. They spread apart, until the body responsible for the constants of physics had to widen its own uncertainty by a factor of 12 and admit that nobody could say why. So how does the most measured force in the universe end up with the worst known number in science? By the end of tonight, you will know exactly. Settle in, subscribe if you haven't yet, because by the end of this, you will not be able to say what the sun weighs, and neither will anyone else. Now, let's slowly slip into this. Part 1. The force you think is finished. Gravity is the one you were never asked to wonder about. Everything else in physics arrives with a warning attached. Quantum mechanics comes wrapped in paradox. Relativity comes with the caution that your intuition will not survive it. The interior of a star, the behavior of light, the structure of an atom, the beginning of the universe. All of these are introduced to you as things that will be difficult, things that will require you to set down what you thought you knew. Gravity is introduced differently. Gravity is introduced as furniture. It was here before the lesson started, and it will be here after. Things fall. You have known this since before you had language for it, and every experience you have had since has confirmed it without a single exception. And there is a story attached, which makes it feel even more finished. A man sits under a tree in the English countryside. An apple comes loose. He looks up, and then out, and understands in one motion that the thing pulling the apple down is the same thing holding the moon in place. It is a good story. Parts of it are even true. Isaac Newton did discuss an apple, late in his life, as a way of describing how the idea first came to him, and the insight underneath it was genuinely one of the most consequential any human being has ever had. The force that makes an object fall off a table and the force that keeps a moon in orbit are not 2 different forces. They are one force, operating on 2 scales, and the difference between a falling apple and an orbiting moon is nothing more than how fast you were going sideways when you started. In 1687, Newton published that idea in the book we now call the Principia, and in doing so, he did something no one had managed before. He wrote down a rule that applied to the entire universe at once. 2 objects attract one another. The attraction grows with the product of their masses. It weakens with the square of the distance between them. Double the distance, and the pull drops to a quarter. Triple it, and the pull drops to a ninth. That relationship, once you have it, lets you calculate the orbit of a planet, the arc of a cannonball, the shape of the tides, and the return of a comet, all with the same handful of symbols. It was the first time anyone had shown that the sky and the ground obey the same law, so the file gets closed. Newton solved gravity in the 1680s. Albert Einstein came along a little over 2 centuries later and refined it, replacing the idea of a force reaching across empty space with the idea of curved space-time. And that refinement was profound. But from the outside, it looks like a finishing touch on something already essentially complete. Gravity gets shelved. It becomes the settled one, the one that does not need you, and every other strange thing in physics gets to have the attention. Here is what that story leaves out. Newton never knew how strong gravity is. I want to be precise about that, because it sounds like a trick, and it is not. Newton's law is a statement of proportionality. It tells you exactly how the force changes when you change the masses and the distance. It does not tell you the size of the force. Written in the form you may have seen, there is a term sitting at the front of the equation, a constant of proportionality, and its entire job is to convert the proportionality into an actual number of actual newtons of actual pull. That term is not in Newton's work. He did not have a value for it. He could not have had one, because measuring it requires detecting the gravitational attraction between two ordinary objects in a room, and nothing in the 1680s was capable of doing that. What Newton had was a shape. He knew how gravity behaves. He did not know how much of it there is. You can go remarkably far without that number, which is part of why its absence went unremarked for so long. Astronomy in particular gets along beautifully without it. If you are tracking a planet around the Sun, the missing constant and the mass of the Sun always appear multiplied together as a single package, and that package is what orbital motion actually responds to. So you can predict eclipses to the second, navigate a spacecraft across the solar system, and calculate the return of a comet a century in advance. And at no point will anyone hand you the strength of gravity, because at no point do you need it. The number hides inside another number and does its work invisibly. But the moment you want to step outside that arrangement, the moment you want to know what the Earth actually weighs, or what the Sun actually weighs, or how hard two objects on a table are pulling on one another, you need the constant on its own. And to get it on its own, someone has to go into a room with two lumps of metal and measure a force so faint that nothing in ordinary human experience prepares you for it. That measurement was first attempted successfully in 1798, roughly 111 years after the Principia. It was carried out by a man working alone in a shed using an instrument built by somebody who had already died. It was, by the standards of its era, one of the most careful pieces of experimental work anyone had ever performed, and it got within about 1% of the modern answer. And then something happened that nobody expected, and that nobody has been able to explain since. Over the following 2 centuries, as instruments improved beyond anything that 18th century experimenter could have imagined, as laboratories were built underground to escape vibration, as lasers replaced telescopes and computers replaced eyes, the measurement of gravity's strength did not converge. It did the opposite. The individual answers got sharper and sharper, each one claiming greater precision than the last. And as they sharpened, they spread apart. They began to contradict one another by amounts far larger than any of them admitted was possible. The strength of gravity is, today, the worst known number in fundamental physics. Not one of the worst. The worst, by a margin so wide it is difficult to convey. And the reason is not that nobody has tried. The reason is that a great many extremely capable people have tried for 228 years with progressively better equipment, and the harder they have looked, the less they have agreed. That is the thing I want to walk you through tonight. Not the story of how we solved gravity, because we did not. The story of how we measured it more and more precisely and understood it less and less as we went. And it starts in a garden shed in South London, with a man so shy he communicated with his own household in writing. Part 2. The Man Who Weighed the World. Henry Cavendish was one of the richest men in Britain, and one of the least visible. He was born in 1731 into an aristocratic family, inherited an enormous fortune, and spent almost none of it. He wore the same style of faded violet coat for decades. He had a staircase built at the back of his house, so that he could come and go without encountering anyone. He communicated with his female household staff by leaving written notes on a hall table, because speaking to them directly was more than he could manage. At meetings of the Royal Society, colleagues learned that the way to get an answer from him was to stand near him and address the general air, never his face, and wait. If you looked directly at him, he would leave. He was also, by a considerable distance, one of the finest experimental scientists who has ever lived. He worked out the composition of water. He isolated hydrogen. He measured the electrical properties of materials with an accuracy that would not be matched for another century, and then, characteristically, did not publish most of it. James Clerk Maxwell went through Cavendish's unpublished notebooks in the 1870s and found result after result that had been independently discovered by other people decades after Cavendish had quietly written them down and put them in a drawer. In 1797, at the age of 66, Cavendish took on the problem that would carry his name. The instrument was not his. It had been designed and built by John Michell, a clergyman and geologist in Yorkshire, who was one of the most quietly original thinkers of the 18th century. Michell had, among other things, worked out that if a star were massive enough, its escape velocity would exceed the speed of light, and nothing it emitted could ever leave it, which is a description of a black hole written in 1783. He built an apparatus to weigh the Earth, and then died in 1793 without ever using it. The instrument passed to another man, and then to Cavendish, who took it apart and rebuilt most of it. The design is called a torsion balance, and the idea behind it is beautiful in its economy. You take a thin wire and hang a light horizontal rod from its center, so the rod dangles like the beam of a scale that has been turned on its side. At each end of the rod, you fix a small lead ball. Now the whole assembly can rotate freely, twisting the wire, and a wire resists twisting only very slightly. That slightness is the point. A wire that barely resists will respond to a force that barely exists. Then you bring two much larger lead spheres close to the small ones, positioned so their gravitational pull acts to rotate the rod. The rod turns, the wire twists. It twists until the wire's resistance exactly balances the gravitational attraction, and then it stops. And if you know how stiff the wire is, and you can measure how far the rod turned, you can work backwards to the force. From the force, you can get the strength of gravity. The small spheres weighed about 1 6/10 pounds each. The large ones weighed roughly 350 pounds each. The rod was about 6 feet long, and the force being measured, the actual physical quantity that had to move that rod, was smaller than the weight of a grain of sand. Which is why the entire experiment is really an exercise in getting everything else out of the way. Picture the shed. It is on Cavendish's property at Clapham, on the southern edge of London, and it is winter. Inside the shed is a wooden case, sealed, and inside the case is the balance. The large spheres hang from a pulley system, whose ropes run out through the wall of the building, because Cavendish has understood something that took other experimenters years to learn the hard way. He cannot be in the room. His body is warm. A warm body on one side of a sealed case sets up a slow convection current inside it, and that current pushes on the rod with a force many times larger than the gravity he is trying to detect. So he stays outside. He turns the pulley from outside, and he reads the deflection through a telescope, aimed through a small hole drilled in the shed wall, with a lamp arranged so that he can see the scale without opening anything. He turns the spheres. Nothing appears to happen. The balance has a natural swing period of about 15 minutes, so the rod does not simply move to a new position, it begins a slow oscillation that takes hours to settle. And Cavendish's job is to sit outside in the cold, with his eye at a hole in a wall, and record where the rod is, again and again, while it drifts through an arc smaller than the width of the pencil he is writing with. He runs the experiment 17 times. He accounts for the gravitational pull of the case itself. He accounts for the magnetism of the iron in the apparatus by swapping in different materials to check. He accounts for the temperature. And when it is finished, he does not calculate the strength of gravity. This is the part that always surprises people. Cavendish never computed the number we now call the gravitational constant. It did not exist as a concept he was pursuing, and he showed no interest in inventing it. His paper is titled, in essence, An Account of Experiments to determine the density of the Earth, and that is exactly what he wanted. He wanted to know what the planet is made of, because if you can measure the gravitational pull of a lead sphere of known size, and you already know the gravitational pull of the Earth, you can compare them, and the comparison tells you how dense the Earth must be relative to the lead. His answer was that the Earth is 5 48/100 times as dense as water. The modern value is 5 514 thousandths. He was off by about 1%. In 1798, in a shed, using an instrument built by a dead clergyman, operated through a hole in a wall by a man who could not bring himself to speak to his own cook. There is a small grace note to this. Newton himself, in the Principia, had guessed at the answer. He reasoned about the density of ordinary surface rock, thought about how much heavier the interior of a planet ought to be under all that pressure, and put the Earth at somewhere between 5 and 6 times the density of water. He offered it almost in passing, as the kind of thing a careful person might estimate on the back of an argument. He was right. He had no instrument capable of testing it, no way of checking, and no expectation that anyone would check within a century of his death, and he landed inside the correct range anyway. His contemporaries understood what had happened. Somebody had weighed the world. Not a mountain, not a region, not an estimate from surface rock. The entire planet, put on a scale, by measuring how hard a lump of lead pulls on another lump of lead in a garden building, and the number that came out was good enough that it stood essentially unimproved for close to 100 years. Weighing the world. Hold on to that phrase, because we are going to come back to it, and by the time we do it, will not mean what it means right now. Because there is a detail hiding inside Cavendish's triumph that nobody in 1798 had any reason to notice, and it is the detail that everything else in this story grows out of. He had measured a density. He had compared one gravitational pull to another gravitational pull, which is a ratio, and ratios are forgiving. Sometime later, other people would want the raw quantity itself, stripped out and standing alone, in units, as a number. And that turns out to be a very different kind of problem. Part 3. The number nobody named. For most of the 19th century, the strength of gravity did not have a name. That sounds like a technicality, and it is not. It is a clue about how physics actually developed, and about why this particular quantity ended up so badly served. Nobody set out to measure the gravitational constant, because for a very long time, nobody was thinking in those terms at all. The question people asked was how heavy the Earth is, or how dense it is, and those are questions about a specific object. They are answerable with ratios and comparisons, and ratios are comfortable. You do not need to commit to a universal quantity to say that the Earth is about 5.5 times as dense as water. The shift happened gradually, over roughly the middle decades of the 1800s, as physics acquired a taste for universal constants. The speed of light became a thing people measured for its own sake. So did the mechanical equivalent of heat. There was a growing sense that the universe had a small number of fixed quantities written into it, and that finding them and pinning them down was the central work of the discipline. Under that view, Newton's law contains one, and it had been sitting there, unexamined, for nearly 200 years. The first serious attempts to pull it out and state it as a number in its own right came in the 1870s, with Cornu and Bayle, in France, among the earliest to compute something recognizably like the modern quantity from a Cavendish-style experiment. The symbol itself, the capital G we now use without thinking, settled into place through the following decades and was firmly established by the 1890s. That decade also produced the first genuine improvement on Cavendish in nearly 100 years, and it came from a man named Charles Vernon Boys. Boys understood something that turns out to matter enormously. Cavendish had hung his apparatus from a wire, and a wire is not a perfect spring. Metal has a memory. When you twist it and hold it and let it go, it does not return exactly to where it started, and it does not resist twisting by exactly the same amount every time. Those imperfections are tiny, and in almost any other application they would be invisible. In this experiment they are the enemy, because the force you are measuring is also tiny, and the two are comparable in size. So Boyes replaced the wire with fused quartz. He learned to draw quartz fibers so fine they were nearly invisible by attaching molten quartz to an arrow and firing the arrow across a room. Quartz behaves far better than metal under torsion. It is closer to a perfect spring. And having a better fiber let him do something counterintuitive. He made the whole apparatus much smaller. That seems backwards. A bigger apparatus with bigger masses generates a bigger force, and bigger forces are easier to measure. But bigger apparatus also means the masses are spread over more space, and every other object in the room, the walls, the floor, the experimenter, pulls on the different parts of a large instrument by different amounts, and those differences do not cancel. Shrink the instrument, and the unwanted gradients shrink faster than the signal you want. Boyes built an instrument you could hold, and got a better answer than a man who had used 350-pound spheres. Now, what actually is this number once you have it? The gravitational constant tells you how much gravity you get per unit of mass at a given distance. Written out, its value is 6.6743 times 10 to the minus 11 in units of cubic meters per kilogram per second squared. The units look strange because they are the units required to take two masses in kilograms and a distance in meters and hand you back a force in newtons. The part to hold on to is that leading factor, 10 to the minus 11. That is a decimal point followed by 10 zeros before you reach the first meaningful digit. Every other headline constant in physics has a value that sits somewhere reasonable when you write it in the units human beings actually use, or has been redefined so that it does. This one is buried 11 decimal places down. That is not a formatting inconvenience. It is a direct statement about how faint the effect is, and therefore about how hard the measurement is going to be. And there is a structural problem baked into the units themselves, which is worth pausing on because it explains most of what follows. Look at what the constant is made of. Length cubed, divided by mass, divided by time squared. There is a mass in there, which means that to determine the constant, you must independently know a mass, precisely, in kilograms. You cannot escape it. Any experiment that gives you the strength of gravity is also, unavoidably, an experiment in weighing things, and it inherits every difficulty that weighing things involves. How uniform is the density of your sphere? Is there a void inside it? Is the surface oxidized? What exactly is the distance between the centers of mass of two objects whose centers of mass you cannot see? This is why gravity's constant is different in kind from the others. When physicists measure the electron's magnetic moment, they are comparing one quantum property against another quantum property, and quantum properties are identical everywhere and forever. When physicists measure the strength of gravity, they are comparing a force to a specific lump of metal that a specific person machined on a specific afternoon, and the lump of metal is the weak link. By the end of the 19th century, then, physics had a name for the number, a symbol for it, a technique for measuring it, and a value accurate to a fraction of a percent. Everything was in place. The obvious expectation, the one that every other quantity in physics had already met, was that the 20th century would take that fraction of a percent and grind it down, decade by decade, into ever finer agreement. For about 80 years, that is roughly what appeared to be happening. And then the good equipment arrived. Part 4. How weak is weak? Before we go any further into the measurements, we need to sit with the size of the thing being measured, because nothing else in this story makes sense until you have felt it. Everyone knows gravity is weak. It is one of those facts that gets stated so often it stops landing. Gravity is the weakest of the four fundamental forces, people say, and you nod, and you file it next to the other things you have agreed to accept. But the word weak is doing an enormous amount of work in that sentence, and it is not doing it honestly, because weak is a human word calibrated to human experience, and this is not a human-scale weakness. This is a weakness of a kind that ordinary language was never built to carry. So let us do it properly. Take 2 1-kilogram weights. Hold one in each hand. A kilogram is a bag of sugar, a large bottle of water, something with real presence in your palm. Now hold them a meter apart, one hand out to each side, and stand still. There is a force between them. It is real, it is happening right now, and it has never once switched off in the entire history of the universe. Every particle in the weight in your left hand is pulling on every particle in the weight in your right hand, continuously, and has been since those atoms formed inside a star. That force is about 6.67 times 10 to the minus 11 newtons, which means nothing to you, so let me convert it. A newton is roughly the weight of a small apple resting in your palm. This force is about 100 billionth of that. If you wanted something to weigh what these two objects pull on each other with, you would be looking for an object with a mass of around 7 billionths of a gram. A grain of table salt weighs about 60 micrograms, which is around 10,000 times heavier than that. A single human red blood cell weighs roughly 100 picograms, and you would need something like 70 of them to match it. So, the gravitational attraction between 2 bags of sugar held a meter apart is comparable to the weight of a few dozen blood cells. And that is what has to be detected. Not inferred, not calculated, physically detected as a real deflection of a real object against a world that is shaking, warming, cooling, and pulling in every other direction at once. Now compare it to its neighbors. Take 2 protons and set them next to each other. They repel each other electrically and they attract each other gravitationally, both at the same time, and the 2 effects are in direct competition. The electrical repulsion wins. It wins by a factor of about 10 to the 36th, which is a 1, followed by 36 zeros. I do not think that number can be felt as a number, so here is the version you already know, without having thought about it this way. Go to your fridge and take a magnet off the door. It weighs a few grams. Hold it above a steel paperclip and watch the paperclip jump up to meet it. In that moment, the electromagnetic field of a small piece of iron you could lose in your pocket has defeated the entire gravitational pull of a planet that weighs 6,000 billion tons. Not narrowly. It is not close. The planet was never really in the contest. That is the force we are trying to measure, and it comes with 2 properties that no other force in physics has, and both of them are catastrophic for an experimenter. The first is that you cannot shield it. Electricity can be shielded. Put a sensitive experiment inside a metal box, and the external electric fields simply stop at the wall, because the charges in the metal rearrange themselves to cancel the field inside. Magnetism can be shielded with the right materials. Sound can be shielded. Light can be shielded. Vibration can be damped. Gravity cannot. There is no material in existence that blocks it, and as far as anyone can tell, there is no material that could. Whatever you build your walls out of, you have added mass, and mass pulls. Shielding a gravity experiment from gravity makes the problem worse by definition. So everything in the room is in the experiment. The concrete floor is in the experiment. The steel in the building's frame is in the experiment. The water table under the foundations rises and falls with the rain, and it is in the experiment. The experimenter's own body, standing 3 meters away, exerts a pull on the apparatus that is a genuine, calculated correction in modern work, which is why in some laboratories, the people running the measurement stand on marked positions on the floor and do not move. The sun is in the experiment, the moon is in the experiment, and the moon moves. The second property is worse. You cannot turn it off. Think about what precision measurement normally looks like. You want to measure a magnetic field. So you record what your instrument reads with the field on, then you switch the field off and record what it reads with the field absent, and the difference between those two readings is your signal. Everything that was contaminating both readings equally has just cancelled. That subtraction is the backbone of experimental physics. It is how you find out what your instrument is doing wrong. There is no off switch for mass. You cannot run a control. There is no configuration of the apparatus in which gravity is absent, so you can see what your errors look like on their own. Every reading you ever take contains the signal and the contamination together, permanently fused, and the only way to separate them is to build a model of every contaminating influence and subtract it by calculation. Which means the quality of your answer depends entirely on the quality of your model of everything else in the world. And here is the consequence, which is the hinge of this whole story. In most experiments, the errors that matter are random. Random errors are almost friendly. They scatter your readings symmetrically around the truth, and if you take enough readings, they average away, and more data always makes you more right. In this experiment, the errors that matter are not random. They are systematic. They come from your particular apparatus, your particular fiber, your particular spheres, your particular room, and they push your answer consistently in one direction. Taking more readings does not remove a systematic error. It just makes you more confident in a wrong number. Which means that when two laboratories using different equipment get different answers, averaging them together does not give you the truth. It gives you a number in the middle of two mistakes, with an error bar that is now lying to you about how well it is known. That is the trap. And in the 1980s and 90s, physics walked straight into it, with the best equipment it had ever built. Part 5. The Disagreement. By the middle of the 1980s, the situation looked good. The Committee on Data for Science and Technology, an international body, usually referred to simply as CODATA, exists to do a specific and rather thankless job. Every few years, it gathers every credible measurement of every fundamental constant, weighs them against one another, and publishes a single recommended value for each, with an uncertainty attached. When a textbook prints a constant, this is where the number came from. When a spacecraft navigation team needs a figure, this is the figure they use. In its 1986 adjustment, CODATA recommended a value for the gravitational constant of 6.67259 times 10 to the minus 11, with an uncertainty of 128 parts per million. 128 parts per million means the value is trusted to about 1 part in 8,000. By the standards of the rest of physics, that is poor, but by the standards of this particular quantity, it was the best anyone had ever done, and more importantly, it looked like the middle of a trend. Measurements from different laboratories were clustering, the error bars were shrinking. The story appeared to be following the normal arc, the arc that every other constant had followed, in which the 20th century slowly and steadily squeezed the uncertainty down. Then a generation of new experiments arrived, built with better materials, better electronics, better vibration isolation, and better ideas, and they did not cluster. In 1995 and 96, a team at the Physikalisch-Technische Bundesanstalt in Braunschweig, Germany, the National Metrology Institute, and one of the most respected measurement laboratories on Earth, published a result using a method nobody had tried before. Rather than hanging the balance from a fiber and letting the fiber's stiffness set the scale, they floated the whole apparatus on a bath of mercury and used electrostatic forces to servo-control it, holding it in place and reading off the electrical effort required. The idea is elegant. If the fiber is the untrustworthy component, remove the fiber. Their claimed uncertainty was a few parts in 100,000, which would have made it competitive with anything in the field. Their value came out about 0.7% higher than the accepted figure. I want to make sure the scale of that lands. 0.7% is 7,000 parts per million. They were claiming a precision of a few tens of parts per million, and landing 7,000 parts per million away from where everybody else was. That is not a disagreement. That is a result sitting so far outside the established range that either the entire prior literature was wrong or something in this beautiful new method was badly misunderstood, and no one could say which. Nobody found the error. Nobody found it in the German result, and nobody found a reason to throw it out. It was a careful measurement by careful people at a serious institution, and it simply did not fit. Meanwhile, other groups were producing results that were individually excellent and collectively incompatible. At the University of Washington in Seattle, a group known as the Eötvös collaboration, named partly for the Hungarian physicist Loránd Eötvös, who had pioneered torsion balance work a century earlier, attacked the fiber problem from the opposite direction. Instead of removing the fiber, they arranged for the fiber never to twist. Their apparatus sits on a turntable, and as the source masses pull on the pendulum, the turntable accelerates to follow it, keeping the fiber at exactly zero twist at all times. If the fiber never bends, its stiffness never enters the answer, and the whole family of errors associated with it disappears. What you measure instead is the angular acceleration of the turntable, which is a much better behaved quantity. That result, published in 2000 by Gundlach and Merkowitz, claimed one of the tightest uncertainties yet achieved. At the International Bureau of Weights and Measures outside Paris, the institution that for over a century physically held the master kilogram, a team led by Terry Quinn built an apparatus that could be run in two different modes, both the classical deflection method and an electrostatic servo method, so that the two could be cross-checked against each other inside one instrument. They published in 2001 and again in 2013. Their values sat high, near the top of the published range. At Gila, in Boulder, Colorado, Parks and Fowler took a completely different approach again, using laser interferometry to track the motion of pendulums with extreme precision. They published in 2010. Their value sat low, near the bottom of the range, many standard deviations away from the Paris results. There was one more hope, and it came from an entirely different direction. Atom interferometry does away with lead spheres and hanging rods altogether. You cool a cloud of atoms until they are barely moving, drop them, and use laser pulses to split each atom's quantum wave into two paths that travel slightly different routes before recombining. The interference pattern that results is exquisitely sensitive to the gravitational field the atoms fell through. Put a large mass nearby, and the pattern shifts. This method shares essentially no systematic weaknesses with any torsion balance ever built, which made it the great hope for breaking the deadlock from outside. It has produced good results. It has not yet produced results precise enough to settle anything. There is also a pattern in the failures that nobody has been able to cash in. Broadly, the experiments split into two families. One family times things. You measure how the oscillation period of a pendulum changes when you move the source masses. The other family holds things still. You measure the force or the torque required to prevent motion from happening at all. Historically, these two families have produced results that sit systematically offset from one another. That is exactly the kind of clue that ought to lead somewhere. It has led nowhere yet. Line them all up, and this is what you see. Each group has spent years, often decades, on a single number. Each has published an uncertainty in the range of tens of parts per million. And the answers are spread across a band roughly 500 parts per million wide, which means the extremes differ by around 0.05%. 0.05% sounds small until you set it against the error bars. A group claiming 20 parts per million precision, whose result differs by 400 parts per million from another group's, is not making a slightly different measurement. It is making a measurement that formally excludes the other one 20 times over. In any other area of physics, a 20 sigma discrepancy would be treated as an emergency or a discovery. Here, it is simply the background condition of the field. They cannot all be right. That is not an opinion, it is arithmetic. And the uncomfortable part is that there is no obvious candidate for the one that is wrong. You cannot point at the outlier and dismiss it, because there are several outliers, and they are outliers in different directions. You cannot appeal to which laboratory is more prestigious, because they are all national institutes and major universities. You cannot appeal to which method is more trustworthy, because the whole reason there are multiple methods is that each was designed to avoid the weaknesses of the others. So the field arrived at a strange and rather quiet crisis. The individual measurements were the best that had ever been made. The spread between them was wider than it had been a generation earlier, when the measurements were worse. The number gets sharper, and the disagreement gets wider. I want you to hold that sentence, because it is going to be the shape of everything that follows, and by the end of tonight, it will turn out to be the answer to the question we started with, rather than just a description of the problem. For now, notice only how backwards it is. In every other corner of science, better instruments produce closer agreement. That is what better instruments are for. That is the entire justification for building them. Here, better instruments produced sharper individual claims that contradicted each other more violently than the blurry old ones ever had, because the blurry old ones had error bars wide enough to overlap. Vagueness had been holding the field together. Precision pulled it apart. Somebody was eventually going to have to stand up and say so officially. In 1998, somebody did. Part 6. The year. The uncertainty went up. Everything I have described so far is the kind of thing that could stay inside the field. Disagreements between laboratories are normal. They get worked out in conference sessions and letters and, eventually, in somebody finding the mistake. Physics is comfortable with unresolved discrepancies for a while, because a while is usually all it takes. What is not normal, what has essentially no precedent among the fundamental constants, is for the disagreement to become so unresolvable that the official record has to be rewritten to admit it. That is what happened in 1998. CODATA published its adjustment that year, and for the gravitational constant, it recommended a value of 6.673 times 10 to the minus 11, with an uncertainty of 1500 parts per million. 1500. 12 years earlier, the figure had been 128. The uncertainty had not been reduced. It had been multiplied by roughly 12. Sit with that for a second, because I think it is easy to hear it as a technical adjustment and miss what it actually is. This is the international body responsible for the numerical constants of physics, publishing its considered judgment, and its considered judgment was that, after more than a decade of additional work by the finest measurement laboratories in the world, using equipment that did not exist in 1986, humanity's knowledge of how strong gravity is had got worse. Not stalled, worse. The honest interval around the answer was now 12 times wider than the interval that had been published before all that work was done. The reason given was stated plainly, and it is worth hearing in something close to its own words. The large increase in uncertainty was necessary because no explanation had been found for the large differences obtained in the presumably more accurate measurements carried out since 1986. Read that phrase again. The presumably more accurate measurements. There is a whole worldview quietly collapsing inside the word presumably. These experiments were more accurate. Everyone involved could describe exactly why they were more accurate, component by component, and the descriptions were correct. Better fibers, better isolation, better electronics, better modeling of the surroundings. Each individual improvement was real, and the collective result of all those real improvements was a set of answers that agreed with each other less well than the cruder answers had. So CODATA did the only defensible thing. It refused to pretend. It could have picked a favorite result and published a tight uncertainty around it, and nobody outside a small community would have noticed. Instead, it published a number with an error bar wide enough to contain the mess, and said, in effect, We do not know why these disagree, so we are going to stop claiming we know this, as well as we said we did. That is intellectual honesty of a fairly high order, and it is also one of the strangest sentences in the modern history of physics. There is no other fundamental constant for which this has happened, not one. Every other number on the list has followed the expected path, tightening decade after decade as instruments improved. Gravity's constant went backwards, in public, in the official record, and it went backwards precisely because the measurements got better. If you want a single moment where the claim in the title of this video stops being a way of speaking and becomes a documented historical event, this is it. In 1998, more precise measurement of gravity produced formerly less certain knowledge of gravity. It is written down. You can look it up. And the instability did not end in 1998. Watch what the recommended value itself has done since. In 1986, it was 6.67259. In 1998, it was 6.673. In 2002, it moved to 6.6742. In 2006, it went to 6.67428. In 2010, it came back down to 6.67428. In 2014, it climbed again to 6.67408. In 2010, it settled at 6.67430, where it remains. Look at what those digits are doing. This is supposed to be a fixed feature of the universe, and the official value for it has wandered up and down the 4th and 5th decimal places for 4 decades, sometimes moving by more than the uncertainty that had been quoted for it the time before. A constant that will not sit still is not misbehaving. The universe is not changing its mind. What is moving is us, and the movement is a record of which measurements happen to be included in which adjustment. And in 2022, CODATA published again and left the value exactly where it was, because in the 4 years since the previous adjustment, no new determination of the gravitational constant had arrived that was good enough to move it. Now, there was one genuine piece of insight that came out of this period, and it is worth understanding because it shows both how the field made progress and why the progress did not help as much as it should have. In 1995, a physicist named Kuroda pointed out something about torsion fibers that had been hiding in plain sight for 200 years. Remember that a whole family of these experiments works by timing. You measure how long the pendulum takes to swing back and forth, then you move the big masses and measure how the period changes, and the change gives you the force. The method assumes the fiber behaves as an ideal spring, storing and returning energy perfectly. Real fibers do not do that. Real materials are slightly anelastic, which means that when you twist them, a small part of the energy is not stored elastically but dissipated internally, and the fiber's effective stiffness depends very slightly on how fast you are twisting it. At the frequencies these pendulums swing at, that effect is small. It is also, Kuroda showed, systematically biased in one direction. Not random, biased. Time of swing measurements would consistently come out too high, by an amount that depended on the fiber. That single observation retroactively put a question mark over an entire generation of published results. It did not tell you what the right answer was. It told you that a specific large group of measurements shared a common flaw, which meant that averaging them together, which everyone had been doing, made things worse rather than better, because the flaw did not cancel. And it explains why the very best modern experiments are designed the way they are. The Seattle turntable that keeps the fiber at zero twist, the Paris servo that holds the balance still with electrostatic force, the German mercury bath that removed the fiber entirely. These are all answers to Kuroda. The field understood the problem and engineered around it. The engineering worked. The disagreement stayed. Which is what makes the next chapter of this story so difficult to shrug off. Because eventually, a group would take the 2 best techniques available the two designed most carefully to avoid each other's weaknesses and run them both, in the same laboratory, with the same masses, under the same conditions, by the same people. You would expect that to settle it. There is essentially nothing left to blame. It did not settle it. Part 7. 2 answers in one cave. There is a hill in Wuhan, in central China, with a laboratory inside it. It belongs to Huazhong University of Science and Technology, and it exists because of a decision made decades ago by a physicist named Jun Luo, who concluded early in his career that if you are serious about measuring gravity, you cannot do it in a normal building. Normal buildings breathe. They warm in the afternoon and cool at night. Traffic outside shakes the floor. Machinery in the basement hums at frequencies that couple into anything hanging from a wire. Air conditioning moves air, and moving air moves apparatus. So the group went underground, into space carved out beneath a hill, where the rock above holds the temperature nearly constant year-round, and the ground is quieter than anywhere at the surface. The environment does not fluctuate. It just sits there, at a stable temperature, in the dark, and the experiment can be left alone for as long as it needs. It needed about 30 years. Let me put that in human terms, because it is easy to say a group worked on something for 3 decades and hear it as a summary rather than a life. A person begins this work in their 30s. They design an apparatus. They discover it is not good enough and design another. They train students who arrive as undergraduates, complete doctorates, and leave for their own careers, and they train the next batch. Above them, the city of Wuhan grows from one thing into another. Underground, the balance swings, and the object of all of it is a number in the 5th decimal place. Picture the room during a run. The apparatus is a torsion pendulum, and everything around it has been engineered to disappear. The temperature is held constant to a small fraction of a degree, because a temperature gradient across the apparatus would drive convection, and convection would swamp the signal. The source masses are spheres, whose density has been mapped, and whose geometry has been measured to a precision that took years of separate work to achieve. The fiber has been characterized, tested, and characterized again. There is nobody in the room, because a person in the room is a mass in the room, and a heat source in the room. And a great deal of the 30 years went not into the pendulum at all, but into the spheres. This is the part of the work nobody imagines. To extract the strength of gravity, you must know the mass of your source objects, and the distance between their centers of mass, and both of those are far harder than they sound. A metal sphere is never perfectly uniform inside. There may be a void you cannot see, a variation in density from how the metal cooled, a slight departure from roundness at the level of micrometers. The center of mass of an object is not a thing you can look at. It has to be inferred from measurements of shape and density, and every imperfection you fail to notice shifts it, and a shifted center of mass changes the distance in the equation, and the distance is squared. Teams working on this problem have spent years characterizing a handful of metal balls. The gravity part of a gravity experiment is often not the hard part. The rod turns through an angle you could not see with your eye against any reference you could name. A sensor reads it. Data accumulates for weeks. Nobody touches anything. And here is the part that makes this experiment different from every other one in the story so far. The group did not run one method, they ran 2. They chose the 2 best techniques available, deliberately, on the grounds that the techniques fail in different ways. The first was the time of swing method, the one Kuroda had warned about, but with the fiber's anelastic behavior, now measured and corrected for directly, using fibers whose properties had been studied specifically for this purpose. The second was the angular acceleration feedback method, in which the whole apparatus sits on a turntable that continuously accelerates to cancel any twist, so that the fiber's stiffness never enters the answer at all. These 2 methods share almost nothing. They depend on different physics, different sources of error, different corrections, different assumptions. If a hidden systematic error were lurking in one of them, there is no reason at all for it to lurk identically in the other. That is the entire point of doing both. It is the cleanest cross-check anyone had ever set up on this quantity, and it was being run by one team, in one place, on one set of masses, in one stable underground environment, with a single shared understanding of every correction being applied. Whatever excuses had been available before were now gone. You could not say the laboratories were different, it was one laboratory. You could not say the masses were different, they were the same masses. You could not say the standards or the technique culture or the local gravity model differed between groups. There was one group. In August 2018, they published the results in Nature. The time of swing method gave 6.674184 times 10 to the minus 11, with a relative standard uncertainty of 11.64 parts per million. The angular acceleration feedback method gave 6.674484 times 10 to the minus 11, with a relative standard uncertainty of 11.61 parts per million. Those are the two most precise determinations of the gravitational constant that have ever been made, both of them. Nothing before or since has been tighter, and they do not agree with each other. The gap between them is about 45 parts per million. Each of them claims to know its own answer to about 12 parts per million. So the two results are separated by something close to 4 times the uncertainty either one of them is willing to admit to. Both values sit within about 2 standard deviations of the internationally recommended figure, so neither one is an embarrassment against the wider field. That is not the problem. The problem is that they are an embarrassment to each other. Two methods chosen precisely because they cannot share a mistake, run by one team who wanted them to agree, produced answers that formally exclude one another. There is something admirable in what happened next, and I want to give it its weight. The team published both numbers. They did not average them into a single value and quote a comfortable uncertainty. They did not hold the results back until the discrepancy could be resolved. They did not quietly favor the one that fitted better with the literature. They put both answers in a major journal, side by side, with the disagreement visible, and left the field to deal with it. That is what science is supposed to look like, and it is also why this result is so much heavier than the ones before it. When two different laboratories disagree, you can always tell yourself a story. Someone's mass metrology was off, someone's local gravity model was incomplete, someone had a fiber problem they did not know about. There is always an explanation waiting to be found, and the search for it feels like progress. When one laboratory disagrees with itself, using two methods designed to have nothing in common, after 30 years of preparation, in a room inside a hill built specifically to remove every excuse, the space where the explanation was supposed to go is empty. Nobody has filled it since. And that is the point in this story, where the question quietly changes shape. Up to here, you could reasonably think of this as a hard measurement problem. Difficult, embarrassing, unresolved, but the sort of thing that better technique eventually cracks. 30 years, 2 methods, 1 cave, and a 45 part per million gap suggests something else. It suggests that the trouble might not be in the instruments at all, which raises a question I have been avoiding, and can avoid for only a little longer. If our best measurements of gravity keep failing to agree, is it possible that the problem is not how we are measuring it, but what we think we are measuring? Before we get there, we need to see how far the consequences of this one uncertain number actually reach. And the answer is going to surprise you, because they reach further than gravity. Part 8. The constant that refused. Let us step back for a moment and put the pieces on the table together, because we are about halfway through, and the shape of this has been building quietly. Newton wrote a law with a missing number. Cavendish, alone in a sealed shed, measured the density of the planet to within 1%, and never calculated the missing number at all. The 19th century extracted it, named it, and improved it. The 20th century built extraordinary machines to pin it down, and those machines disagreed with each other more violently than the crude ones had. In 1998, the official uncertainty was multiplied by 12 because nobody could explain why. And in 2018, a group inside a hill in Wuhan ran the 2 best techniques ever devised, deliberately chosen so they could not share a mistake, and got 2 answers separated by 4 times their own error bars. The number gets sharper, and the disagreement gets wider. Now I want to show you what that has cost, institutionally, because there is a moment where physics had to formally acknowledge this in the structure of measurement itself. On the 20th of May, 2019, the International System of Units was redefined. This was one of the largest changes in the history of measurement, and it received a fraction of the attention it deserved. For most of the modern era, some of our base units were defined by physical objects or physical procedures. The kilogram was the worst offender. Until 2019, the kilogram was a lump of platinum-iridium alloy sitting in a vault outside Paris, and the definition of a kilogram was, literally, the mass of that object. If it gained a fingerprint of contamination, the kilogram got heavier, everywhere in the universe, by definition. Copies of it distributed around the world had drifted measurably away from the original over a century, and nobody could say whether the copies had gained mass or the original had lost it, because there was nothing more fundamental to check against. The 2019 redefinition ended that. Instead of defining units by objects, physics turned the logic around and defined units by constants of nature, fixing those constants to exact values with no uncertainty at all, forever. The Planck constant was fixed to an exact number, and the kilogram now follows from it. The elementary charge was fixed exactly, and the ampere follows. The Boltzmann constant was fixed exactly, and the Kelvin follows. The Avogadro constant was fixed exactly, and the mole follows. The speed of light had already been fixed exactly back in 1983, which is why the metre is now defined as the distance light travels in a specified fraction of a second. These constants are no longer measured, they are decreed. Their uncertainty is precisely 0, because they are definitions, and everything else in metrology is built on top of them. Newton's gravitational constant was not included. It could not be. To fix a constant by definition, you have to know it well enough that fixing it does not create absurdity, and gravity's constant is not known anywhere near well enough. 22 parts per million is not a foundation. So when physics rebuilt the entire structure of measurement on a bedrock of exactly known constants, gravity was left standing outside the building, still an experimental quantity, still something you have to go into a room and try to measure, still uncertain. It is, in that specific sense, the last one. The great project of the 20th century was to replace measured standards with fixed natural constants, and it succeeded almost completely. Gravity is the holdout, the oldest force in physics, the first one described mathematically, the one everybody thinks is finished, is the one that could not be brought inside. Now, this is exactly the sort of situation that attracts alternative explanations, and I want to deal with those honestly rather than pretend they do not exist, because some of them come from serious places. The most persistent is the idea that the constant is not constant, that gravity's strength changes over time, and the reason laboratories disagree is that they are measuring a moving target. This is not a silly notion, and it did not originate at the fringe. Paul Dirac, one of the founding figures of quantum mechanics, proposed something along these lines in 1937. He had noticed that certain enormous dimensionless numbers you can construct from physical constants come out suspiciously similar in magnitude, and he suggested this could not be coincidence, and that the way to make it non-coincidental was for the strength of gravity to decrease slowly as the universe ages. It was a serious idea from a serious person, and it made a testable prediction. It has been tested thoroughly, and it fails. The most elegant test uses the moon. The Apollo missions left retroreflectors on the lunar surface, arrays of corner mirrors that bounce a laser pulse straight back to its source. Fire a laser from Earth, catch the returning photons, time the round trip, and you can measure the Earth-Moon distance to within centimeters. Do that for decades, and you have a record of the lunar orbit of extraordinary precision. If the strength of gravity were weakening, the Moon's orbit would slowly expand in a very specific way, and it does not. Lunar laser ranging constrains any fractional change in the gravitational constant to well under 1 part in 10 to the 13th per year. Binary pulsar timing gives an independent constraint. The physics of the early universe gives another. So we arrive at a genuinely strange position. We can demonstrate that the strength of gravity is not changing, to a precision of better than 1 part in 10 trillion per year. We cannot say what the strength of gravity is, to better than about 1 part in 50,000. We know it is not moving far, far better than we know where it is. There is a related claim that surfaces periodically, suggesting the historical scatter in gravity measurements shows a hidden pattern, sometimes proposed as a cycle linked to the length of the day. These analyses have not survived examination. The apparent pattern depends heavily on which measurements are included and which are left out, and no mechanism has been offered that has any independent support. And then there is the oldest one, which is the idea that gravity can be blocked or reversed by some device. Claims of gravity shielding recur every couple of decades, usually involving spinning something. None has ever been replicated by an independent laboratory. Careful attempts to reproduce the most publicized case found nothing at all. I think all 3 of these share an impulse worth naming, because the impulse is understandable. Each is an attempt to convert a boring and humiliating truth into an interesting one. The boring truth is that this measurement is genuinely, structurally, brutally hard, and that 100 careful people can fail at the same task for 200 years without anybody hiding anything. But there is one consequence of that boring truth that is not boring at all, and we have not looked at it yet. Because if you do not know the constant, there is something enormous that you also do not know. Something you were told in school, something you have never once doubted, and something that nobody on Earth has ever actually measured. Part 9. We do not know what the sun weighs. Here is a fact you have almost certainly been told, probably more than once, and have never had any reason to question. The sun has a mass of about 2 times 10 to the 30th kilograms, roughly 2,000 billion tons. It is in every textbook, every reference table, every documentary. It is one of those numbers that feels like bedrock. Nobody has ever measured it. I do not mean that nobody has measured it very well. I mean that the quantity astronomers actually determine when they study the solar system is not the mass of the sun, has never been the mass of the sun, and cannot be made into the mass of the sun without passing through the least reliable number in physics. Let me show you exactly where this comes from, because once you see it, you cannot unsee it, and it applies to everything in the sky. Go back to Newton's law. The force between 2 objects is the gravitational constant, times the first mass, times the second mass, divided by the distance squared. Now put a planet in orbit around a star, and ask what determines the orbit. The planet's own mass drops out of the problem almost entirely, for the same reason a heavy ball and a light ball fall at the same rate. What is left governing the motion is a single combined quantity, the gravitational constant, multiplied by the mass of the star. That product has a name. It is called the standard gravitational parameter, and it is written as G times m. And here is the crucial thing about it. When you watch an orbit, that product is what you are measuring, not the constant, not the mass. The 2 of them fused into one number, and there is no observation of orbital motion, however precise, that can pull them apart, because orbits simply do not care how the product is divided between its factors. Now, We can measure that product superbly. For the Earth, the standard gravitational parameter is known to something like 2 parts in 10 to the 9th. 2 parts in a billion. That precision comes from decades of tracking satellites with laser ranging, from spacecraft telemetry, from radar, from the accumulated work of 1,000 people who needed to know exactly how the Earth pulls in order to put things in orbit and keep them there. It is one of the best determined quantities in all of physical science. For the Sun, the equivalent parameter is known even better. Spacecraft have been navigating the solar system for over 60 years, and their trajectories are exquisitely sensitive to it. We know the Sun's gravitational parameter to something like 10 significant figures. So we know the pull of the Sun to 10 digits. Now try to get the mass. You take that beautifully determined product and you divide it by the gravitational constant. And the gravitational constant is known to 22 parts per million. Every digit beyond the 4th or 5th is destroyed instantly. It does not matter that the numerator was known to 10 figures. When you divide a number known to 10 figures by a number known to 5, you get a number known to 5. The precision does not survive contact, so the mass of the Sun, and the mass of the Earth, and the mass of Jupiter, and the mass of every star whose weight has ever been inferred from the motion of a companion are all known to roughly 1 part in 10,000, 4 digits, and every single one of those numbers is limited by the same thing, not by our telescopes, not by our spacecraft, not by our theory, but by 2 lead spheres on a bench that nobody can agree about. Sit with that for a moment. The Sun is the most observed object in the history of human attention. We have watched it every day for as long as there have been eyes. We have instruments in orbit around it. We have flown a probe through its outer atmosphere. We can tell you the composition of its surface, the temperature of its core, the frequency of its oscillations, the age of it to within a few tens of millions of years. We cannot tell you what it weighs to better than 4 figures. Not because the Sun is hiding anything, because 1798 happened in a shed, and the problem it opened has not been closed. The gap between the 2 numbers is not a fact about the Sun at all. It is a fact about us. 6 digits of precision exist in the measurement and are thrown away at the last step, and the place they are thrown away is a laboratory on Earth where somebody is trying to weigh a metal ball. There is a lovely historical detail buried in here, which is that astronomy figured out how to sidestep the problem long before anybody understood it was a problem. Kepler's third law, in its exact modern form, contains the standard gravitational parameter rather than the mass. So the entire edifice of celestial mechanics, all the way from the 17th century through to the space age, was built on a quantity that never required knowing the strength of gravity. This is why Cavendish could be a century late to the party without holding anything up. It is why mission planners today work in units of the gravitational parameter and never convert to mass, because converting would only lose them precision they need. The whole discipline roots around the damage without comment, as a matter of ordinary professional practice. Which means that if you are a navigator flying a spacecraft to Jupiter, you genuinely do not care what Jupiter weighs. You care how hard it pulls, you know that superbly, and the mass is a piece of trivia you would only need if somebody asked you at a party. The trouble arrives the moment the mass itself is the thing you want to know, and there are places where that matters enormously. Stellar physics depends on mass, how a star burns, how long it lives, whether it ends as a white dwarf or collapses further. All of it is set primarily by mass. Models of stellar structure are built and tested against measured masses, and those masses carry gravity's uncertainty inside them. The same is true one level up, where the mass of a galaxy is inferred from the motion of the things inside it, and one level up again, where the mass of a cluster of galaxies is inferred from the motion of the galaxies. The uncertainty propagates outward, quietly, all the way to the largest structures we can see. Every mass in the universe, as we have written it down, rests on a number that two laboratories in the same cave could not agree on. And that would be the end of it, if the constant were the only thing in doubt. But the constant is only the front of the equation. Sitting behind it is the law itself, the inverse square, the relationship Newton actually discovered, and there is a question about that, which is much less comfortable than anything we have discussed so far. How much of the range of distances in this universe has that law actually been tested across? The answer is a narrow band in the middle, with darkness at both ends. Part 10. The law at the edges. Newton's inverse square law says that gravity weakens with the square of distance. Double the separation, quarter the force. We have been treating that as given all night, as everyone does, and it is worth asking the obvious question about it. Over what range of distances has anyone actually checked? Start at the small end. Testing gravity between objects a few centimeters apart is already the delicate business we have spent this whole video describing. Push the separation down to a millimeter and it becomes far worse, because as the gap shrinks, other forces that were negligible start to dominate completely. Static electricity on the surfaces, patch potentials, which are tiny variations in the electrical character of a metal surface from one spot to the next, invisible and unavoidable. And at the smallest separations, the Casimir force, a genuine quantum effect in which two closely spaced plates are pushed together by the structure of the vacuum between them, which rises steeply as the gap closes. Every one of those is larger than gravity in that regime. So the experiment becomes a matter of building shields, choosing coatings, and designing geometries that cancel the interlopers, in the hope of exposing a gravitational signal underneath. The group that has pushed hardest at this is the EOT-WASH collaboration in Seattle, the same people who built the turntable that keeps the fiber at zero twist. Their short-range work uses pendulums shaped like discs, with holes bored through them, so that as a source disk rotates beneath the pendulum, the gravitational pull rises and falls at a known frequency, letting them pull the signal out of the noise by looking only at that frequency. In a result published in Physical Review Letters in 2020, they tested the 1/r² behavior of gravity down to separations of about 52 micrometers. 52 micrometers is roughly the width of a fine human hair. Down to that distance, gravity behaves exactly as Newton said it does, no deviation. Below it, we do not know, not because anyone doubts it, because nobody has been able to look. And that unexamined region is not theoretically empty. In the late 1990s, a proposal from Arkani Hamed, Dimopoulos, and Diwali suggested that there might be additional spatial dimensions, curled up small, which gravity can spread into, but the other forces cannot. If that were true, then at separations smaller than the size of those dimensions, gravity would appear to strengthen faster than the inverse square, because the field would be spreading into more directions than we can see. The motivation for the idea is one of the ugliest open problems in physics, and it deserves naming here because it will come back. Gravity is roughly 10 to the 36th times weaker than the other fundamental forces. Nobody knows why. There is no mechanism in any accepted theory that produces a number like that. It is not derived, it is observed, and it sits there as an enormous, unexplained ratio at the center of the discipline. This is called the hierarchy problem, and extra dimensions were one attempt to dissolve it by proposing that gravity is not actually weak at all, but merely diluted, leaking into dimensions we cannot access. Short-range experiments have squeezed the room available for that idea substantially. Work of this kind has established that no extra spatial dimension can be larger than a couple of 100 micrometers across, which sounds like a loose constraint until you remember that a decade earlier, the honest answer was that nobody had any idea, and that a dimension a millimeter wide was a live scientific possibility. That is real progress. It is also progress by elimination, which tells you where something is not, and never where it is. They have not closed it. Below 52 micrometers, the law is a reasonable assumption rather than a measured fact. Now go the other way. Out at the scale of a galaxy, the inverse square law does not merely become untested, it gives the wrong answer. The observation is straightforward, and has been for a long time. Take a spiral galaxy, measure how fast stars orbit at different distances from the center, and compare that to what the visible matter should produce. In the solar system, planets further out move more slowly, which is exactly what gravity predicts. In a galaxy, they do not. The rotation curve flattens out. Stars in the outer regions move about as fast as stars much further in, and far faster than the visible mass can account for. At those speeds, they should have been flung out into intergalactic space long ago. They are still there. Fritz Zwicky noticed a version of this for clusters of galaxies in the 1930s and coined a term for the missing mass. He was largely ignored. In the 1970s, Vera Rubin and Kent Ford measured rotation curves for individual galaxies carefully enough that the result could no longer be dismissed, and the field had to reckon with it. There are exactly two ways out, and physics has been arguing about them ever since. The first is that most of the matter is invisible. There is 5 or 6 times as much mass in a galaxy as we can see, made of something that does not emit, absorb, or reflect light, and interacts with ordinary matter essentially only through gravity. This is dark matter, and on the largest scales the evidence for it is strong. The bullet cluster, catalogued as 1E0657-56, is the case usually cited. 2 clusters of galaxies that have collided, in which the hot gas, which is most of the ordinary matter, has been slowed by the collision and left behind in the middle, while the gravitational mass, measured by lensing, has sailed straight through and sits out with the galaxies. Mass and visible matter have been physically separated. That is difficult to produce with any modification of gravity's law. The second way out is that there is no missing matter, and the law of gravity is simply wrong in this regime. In 1983, Mordechai Milgram proposed modified Newtonian dynamics, which keeps the matter we can see and changes the rule instead. The proposal identifies a characteristic acceleration around 1.2 times 10 to the minus 10 meters per second squared, and says that above that acceleration Newton holds, while below it, gravity falls off more slowly than the inverse square. That acceleration is absurdly small. It is roughly the rate at which your speed would increase if it took you about 250 years to reach walking pace. Nothing in the solar system ever gets that low, which is why the solar system shows no sign of any of this. Now, the honest scorecard, because this is a real dispute between serious people and I do not want to flatten it. Modified dynamics does something genuinely remarkable at the scale of individual galaxies. From the visible matter alone, it predicts the rotation curve, including detailed wiggles that track the visible structure, with a single parameter. Dark matter models can reproduce those curves too, but generally by fitting a halo to the data afterward, rather than predicting it in advance. There is a documented regularity here, often called the radial acceleration relation, showing that the observed acceleration in a galaxy is tightly determined by the visible matter alone. Modified dynamics predicts that relation as a matter of course. Dark matter has to explain why it emerges, and then modified dynamics fails. It does not work on clusters of galaxies without adding some unseen mass anyway, which rather defeats the purpose. It has no clean account of the detailed structure of the cosmic microwave background, which dark matter models fit with startling accuracy. It struggles with how structure formed in the early universe. Meanwhile, dark matter succeeds everywhere. Modified dynamics fails, and has one enormous problem of its own. After 4 decades of increasingly sensitive searches, in shielded underground detectors, in particle colliders, and in the sky, nobody has ever directly detected a particle of it. The experiments have grown more sensitive, by many orders of magnitude, and returned nothing. The space where the particle was supposed to be has been narrowed and narrowed, and the particle has not appeared. So the position we are in, honestly stated, is this. One explanation works beautifully on galaxies and fails on everything larger. The other works beautifully on everything larger and has never been seen. Both are, at bottom, admissions of the same thing. Applied to a galaxy, our description of gravity does not close. It needs either an ingredient we cannot find or a modification we cannot justify. We began this video unable to say how strong gravity is. We have now arrived somewhere considerably less comfortable, which is that we may not be certain of the shape of the law either. Above and below, a fairly narrow band of distances, in the middle, where all our tests happen to live. And there is one more scale to check, the largest one, because when you go all the way out, past galaxies, past clusters, to the universe itself, gravity does something that ought to be impossible. It stops pulling. Part 11. The Force That Pushes. In 1998, two independent groups of astronomers set out to measure how much the expansion of the universe has been slowing down. The question seemed settled in advance. The universe has been expanding since the beginning. Everything in it has mass, mass attracts, and so the expansion must be decelerating. The only real question was by how much, and the answer to that would tell you the fate of everything, whether the universe expands forever at an ever slower rate, or eventually reverses and falls back together. To measure it, both teams used a particular kind of exploding star. A Type 1 supernova occurs when a white dwarf accumulates matter until it crosses a threshold and detonates. And because that threshold is essentially the same everywhere, these explosions have close to the same intrinsic brightness wherever they happen. That makes them a distance marker. Compare how bright one looks to how bright it should be, and you know how far away it is. Measure the stretching of its light, and you know how much the universe has expanded since it exploded. Do that for enough supernovae at enough distances, and you can reconstruct the expansion history. Both teams found the same thing, and neither of them believed it at first. The distant supernovae were fainter than they should have been. Not by much, but consistently, and in a pattern that had only one straightforward reading. The expansion of the universe is not slowing down. It has been speeding up. Something is pushing. I want to be careful about the language, because this is a place where casual description does real damage. Nothing is literally shoving galaxies apart like a hand. What is happening is that the expansion of space is accelerating, and in the mathematics of general relativity, that requires a component of the universe's contents with a strange property. Ordinary matter and radiation have positive pressure. This component has negative pressure, and in Einstein's equations, negative pressure produces repulsive gravitation. So at the largest scale, the dominant gravitational effect in the universe is not attraction, it has the opposite sign. The name assigned to whatever is doing this is dark energy, and the name is a placeholder standing in for our ignorance, in exactly the same way dark matter is. What we can say is how much of it there is. It accounts for roughly 68% of the total energy content of the universe. Dark matter accounts for around 27%. Everything else, every star, every planet, every cloud of gas, every atom in your body, and every atom that has ever been detected by any instrument, makes up about 5%. The whole of the material universe, as we have ever known it, is a rounding error in the accounting. In general relativity, there is a natural way to write this in. Einstein's field equations permit an extra term, a constant, which acts uniformly everywhere and produces exactly this kind of behavior. Einstein put it in himself, in 1917, for the opposite reason. He wanted a static universe, and the equations without it insisted on a dynamic one, so he added a term to hold everything still. When the expansion of the universe was demonstrated observationally, he took it out again. It came back in 1998, doing the reverse of the job he had first given it. Now here is where this becomes a story about our understanding rather than about the universe. If there is a constant energy associated with empty space, quantum field theory ought to be able to tell you how large it is. Empty space, in quantum field theory, is not empty. It has structure. Fields exist everywhere, and they fluctuate. And those fluctuations carry energy, and that energy should gravitate. So you calculate it, and the calculation gives a number. The number is wrong. Not slightly wrong. It exceeds the observed value by something in the region of 120 orders of magnitude. 120 orders of magnitude is a 1, followed by 120 zeros. There is no analogy that survives this. If you try to compare it to the size of the observable universe measured in the width of a proton, you have used up about 40 orders of magnitude, and you are nowhere near. There are fewer atoms in the observable universe than this by a very wide margin. It is routinely and fairly described as the worst quantitative prediction in the history of science, and the description is not a joke at anyone's expense. The calculation is done using our best theory of matter, applied to the simplest possible situation, empty space, and the answer is off by a factor with 120 zeros in it. There are technical arguments about the right way to do the sum and whether the discrepancy should be quoted as 120 or some smaller, enormous number. None of them makes it small. There is a story, repeated often, that Einstein called the cosmological term his greatest blunder. The phrase reaches us second-hand, through George Gamow, and historians have never been able to confirm he said it. What is documented is that he abandoned the term once the expansion was established and considered the episode a mistake of judgment rather than of mathematics. The term was never wrong. He had simply used it to hold the universe still, and the universe declined. Something is very badly wrong in how quantum theory and gravity are being made to speak to each other, and this is the loudest available signal of it. And there is a second oddity layered on top, which physicists sometimes call the coincidence problem. Dark energy has a roughly constant density as the universe expands, because it is a property of space itself, and there is always more space. Matter does the opposite. As space stretches, the same matter is spread thinner, so its density falls. That means the two have been on opposite trajectories for the whole history of the universe. Early on, matter overwhelmingly dominated. Far in the future, dark energy will overwhelmingly dominate. There is only one relatively brief window in the entire history of the cosmos in which the two are comparable in magnitude. We are in it. That may be a genuine clue, pointing at some mechanism that links the two. It may be pure selection, in the sense that this is also roughly the era in which stars and planets and observers exist, so perhaps no one was ever going to be around to notice any other epoch. Or it may be a coincidence, which is the least satisfying answer available and cannot be ruled out. Nobody knows which. Let me now put the three scales side by side, because the pattern is the point. On a laboratory bench, where we can control everything, we cannot agree on gravity's strength to better than a few hundred parts per million, and 30 years in a cave produce two answers that exclude each other. At the scale of a galaxy, the law we have gives the wrong answer unless we add 5 times more matter than we can see, or change the law in a way nobody can justify from first principles. At the scale of the universe, the sign flips, and our best theoretical account of the responsible quantity is wrong by 120 orders of magnitude. 3 scales, 3 failures, 3 completely different kinds of failure. And notice something about the middle of that list. The uncertainty in the gravitational constant, the thing we have spent most of tonight on, does not even matter at the largest scales. 22 parts per million is nothing next to a factor with 120 zeros. The measurement crisis and the cosmological crisis are not the same size at all. They are not even in the same universe of size. What they share is their direction. And the reason I want them lined up like that is that it starts to look less like a series of unrelated technical problems and more like one problem seen from three angles. In each case, we have a description that predicts behavior superbly within the range where it was calibrated, and breaks down or requires unexplained additions the moment it is taken outside that range. That is what a description does. It is not what an explanation does. Which brings us to the thing we have been circling all night without saying directly. We have been talking as though the difficulty is measuring gravity, or testing gravity, or extending gravity to new scales. Underneath all of that is a simpler and more uncomfortable fact about the theory itself. General relativity is the most accurately confirmed theory in the history of physics. And it does not say what gravity is. Part 12. A theory with no mechanism. I want to be completely fair to general relativity before I say anything critical about it, because its record is extraordinary, and nothing in what follows is a complaint about its accuracy. Einstein published the field equations in 1915. Almost immediately, they explained something that had been quietly bothering astronomers for over half a century. The orbit of Mercury precesses. The whole ellipse slowly rotates around the Sun, and most of that rotation is accounted for by the pull of the other planets. But a residue of about 43 arcseconds per century had refused to be explained. People had proposed an undiscovered planet to account for it, and given it a name, and looked for it, and not found it. General relativity produced the missing 43 arcseconds with no adjustable parameters. The theory was not fitted to that result. The result fell out. Then the predictions started arriving. Light bends when it passes a massive body, and by twice the amount Newtonian reasoning gives. Confirmed by observation of a solar eclipse in 1919 and refined 1,000 times since. Clocks run slower in stronger gravitational fields, which sounds like an abstraction until you remember that the satellite navigation system in your pocket would drift by kilometers per day if the effect were not corrected for continuously. A rotating mass drags space-time around with it, which was measured directly by a dedicated satellite mission and by laser ranging to others. Massive objects can collapse to a state from which nothing escapes, and we have now photographed the shadow of two of them. Accelerating masses radiate ripples in space-time that carry energy away, and the orbital decay of a binary pulsar matched the predicted rate to within a fraction of a percent for decades before anybody detected those ripples directly. Every one of those was a prediction first and an observation second. That is as good as physics gets. By the standard of predictive accuracy, general relativity may be the most successful theory human beings have ever produced. Now, here is the thing nobody tells you about it. It does not say what gravity is. General relativity says that mass and energy curve space-time, and that objects move along the straightest available paths through the curved geometry that results. It specifies the relationship between the contents of a region and the curvature of that region with total precision, and from that specification, everything above follows. But ask the next question. Why does mass and energy curve space-time? By what mechanism? What is the process by which the presence of a lump of matter causes the geometry around it to change? General relativity has no answer. It does not attempt one. The field equations are a statement of correspondence, not of causation. They tell you that this amount of energy goes with that amount of curvature, the way an exchange rate tells you what a currency is worth without telling you anything about why. This is genuinely unusual, and the comparison with the other forces makes it obvious. Electromagnetism has a mechanism. Charged particles interact by exchanging photons. That is not a metaphor or a bookkeeping device. It is a physical account of what is happening, and it makes quantitative predictions of terrifying accuracy. The electron's magnetic moment has been calculated from that account and measured experimentally, and theory and experiment agree to 12 significant figures. That is the most precisely verified prediction in all of science, and it rests on a story about what the force actually is and how it is transmitted. The strong and weak nuclear forces have equivalent accounts, with their own carrier particles. 3 of the 4 forces have a description and an explanation. Gravity has a description of unparalleled quality and no explanation at all. It is a theory that tells you what and refuses to tell you why. Hold that phrase. We are going to come back to it, and it is going to mean something larger by the end. The obvious move, the one physics has been attempting since roughly the 1930s, is to give gravity the same treatment that worked for the others. Quantize it, find its carrier particle, write down a quantum field theory of gravity, run the machinery, and extract predictions. It has never worked. The technical reason has a name, and the name is renormalization. When you calculate anything in quantum field theory, you find yourself summing over an infinite range of possible intermediate processes, and the sums come out infinite. This happens in electromagnetism too. The trick that rescues electromagnetism is that all those infinities can be absorbed into a finite number of measured quantities, like the electron's mass and charge. You measure those once, experimentally, and every infinity in the theory disappears into them. After that, the theory predicts everything else cleanly and forever. That is what it means for a theory to be renormalizable. Gravity is not renormalizable in that sense. When you attempt the same procedure, the infinities do not fall into a finite set of buckets. Each order of the calculation produces new kinds of infinity, requiring new quantities to absorb them, and the number of quantities you would have to measure experimentally is unbounded. A theory that requires infinitely many measured inputs before it can predict anything is not predicting anything. Underneath the technical failure sits a conflict of temperament between the two theories, and it is worth seeing plainly, because it is the reason the marriage has never taken. General relativity is a theory of smooth, continuous geometry. Space-time in general relativity is a surface, differentiable everywhere, with a definite shape at every point. Quantum mechanics is a theory in which definite values are the exception. Things do not have positions until something forces the question. Quantities fluctuate, and the fluctuations are not ignorance about a hidden truth, they are the truth. Now put the two together, and watch what happens. Take a single atom, and place it in a superposition of two locations, which is an ordinary laboratory procedure done thousands of times a day. The atom has mass. Mass curves space-time. So where is the curvature? There is no available answer. You cannot say the curvature is in both places, because general relativity does not permit space-time to have two shapes at once. You cannot say it is in neither, because the mass is real. You cannot say the atom's position resolves first, because nothing in quantum mechanics privileges gravity that way. The question is perfectly reasonable, requires only physics that both theories claim to govern, and cannot be answered by either. That is not a gap in a calculation. That is two descriptions of reality that cannot both be about the same world. For a while, it was possible to hope that the divergence was an artifact of doing the calculation badly, and that at some order things would tidy themselves up. In 1986, Goroff and Sagnotti carried out the calculation for pure gravity at second order and showed explicitly that the divergence is there and cannot be absorbed. The hope closed. That result is why the serious candidate theories look the way they do. String theory proposes that the fundamental objects are not points but extended, which softens the short-distance behavior that generates the infinities. Loop quantum gravity proposes that space-time itself is granular at the smallest scale, so that the infinitely small distances driving the divergences do not exist to begin with. Both are enormous intellectual structures built by serious people over decades. Neither has produced a single prediction that has been experimentally tested and confirmed. That is not an accusation of failure on the part of the theorists. It is a statement about where the relevant physics lives. The energy scale at which quantum gravitational effects should become obvious is something like 15 orders of magnitude beyond the reach of the most powerful particle accelerator ever built. Closing that gap with current approaches would require an accelerator of a size that is not merely expensive, but geographically implausible. So the situation is this: we cannot measure the constant reliably. We cannot verify the law at the smallest and largest distances. We cannot explain why the force is so weak. We cannot say what the force is, and we cannot quantize it, because the mathematics refuses and the experiments are out of reach. At which point a reasonable person asks the obvious question: if we cannot get at this theoretically, can we get at it experimentally from the other end? Forget the accelerator. If gravity is quantized, there should be a particle. Find the particle. There is a name for it. It has been named since the 1930s, and there is a very good argument that we will never catch one. Part 13. The particle we may never catch. If gravity is a quantum field like the others, it has a quantum, a smallest possible unit, a particle. We know a surprising amount about what that particle would have to be like, purely from the behavior of gravity itself, without ever having seen one. It has to be massless, because gravity reaches across the entire universe without weakening beyond the inverse square. A force carried by a massive particle has a limited range, which is why the weak nuclear force does not reach past the inside of a nucleus. Gravity reaches everywhere. Its carrier weighs nothing. It has to have a spin of 2, and that is the more interesting requirement. Spin, in this context, is a property describing how a particle's field behaves under rotation, and it determines something you would not expect it to determine: who attracts whom. A spin 1 carrier, like the photon, produces a force in which like charges repel and opposite charges attract. That is why electricity comes in 2 flavors that cancel. A spin 2 carrier produces a force in which everything attracts everything, with no cancellation available, because there is only one kind of gravitational charge, and it is positive mass energy. That single fact explains something about the universe you have taken for granted your whole life. Electromagnetism is by far the stronger force, and yet the universe is not organized by it, because positive and negative charges sit next to each other and cancel out almost perfectly at any distance. Gravity has nothing to cancel against. Every gram adds. So the weakest force, given enough matter and enough time, is the one that builds planets and stars and galaxies, simply because it never stops accumulating, while the strong one keeps neutralizing itself. The particle even has a name, which it acquired in the 1930s, long before anyone had a coherent theory to put it in. It is called the graviton. Nobody has ever detected one, and there is a serious argument, made by serious people, that nobody ever will. The argument is usually traced to Freeman Dyson, who was blunt about it. His position was not that graviton detection is technically difficult. It was that no conceivable experiment in the real universe could accomplish it, which is a much stronger claim, and one that would place the question permanently outside the reach of science rather than merely beyond our current means. The claim was examined properly rather than left as an aphorism. Tony Rothman and Stephen Bown worked through it in detail in a paper published in Foundations of Physics in 2006. Their finding was carefully stated and worth repeating accurately. It is possible, they concluded, to construct an idealized thought experiment in which a single graviton is detected. But once anything remotely resembling realistic physics is taken into account, the detection becomes impossible. Their assessment was that Dyson's conjecture is very likely true. The obstacles compound in a way that is almost comic. Gravity's coupling to matter is so absurdly feeble that the probability of any given atom absorbing any given graviton is beyond negligible, so your detector has to be enormous. Make it enormous, and it becomes massive, and if you keep going, a detector of sufficient mass, concentrated in one place, simply collapses under its own gravity into a black hole, which is not a useful instrument. Meanwhile, any environment producing gravitons in quantity is also producing neutrinos in overwhelming quantity, and neutrinos interact far more readily than gravitons do, so the signal you want arrives buried under a flood of something you do not. Shield against the neutrinos, and you have added more mass to a detector that was already collapsing. The problem is not engineering. Every approach fails for a different reason, and the reasons are all reasons of principle. So this is the position. The theory cannot be quantized mathematically. The energy scale where it would matter is 15 orders of magnitude beyond our reach, and the particle that would settle the question by direct evidence appears to be undetectable, not because we are not clever enough yet, but because the universe seems to be arranged so that it cannot be caught. There are cleverer indirect approaches under development, aiming to demonstrate that gravity is quantum without ever catching its quantum, by showing that gravity can do something only a quantum field could do. Those efforts are real and ongoing, and some of them are beautiful. None has succeeded yet, and the required sensitivities remain far beyond current capability. It is worth pausing on the alternative, because it is rarely stated, and it is not absurd. Everyone assumes gravity must be quantum, on the grounds that everything else is, and the universe presumably does not run on two incompatible operating systems. But that is an assumption, not a result. A minority of physicists have taken seriously the possibility that gravity is genuinely classical all the way down, that space-time really is a smooth, continuous thing and does not fluctuate, and that the correct picture has quantum matter sitting on a non-quantum stage. Most of the field regards that as thoroughly unattractive, and there are strong arguments against it. But notice the shape of the situation. We cannot prove gravity is quantum, we cannot catch the particle that would prove it, and we cannot rule out the alternative either. The most basic question you could ask about this force, whether it belongs to the same category of thing as everything else in physics, is open. And underneath all of it, unexplained, sits the number we have brushed past twice tonight and now need to look at directly. Go to your kitchen, take a magnet off the fridge. It is a small thing, a few grams, a piece of plastic-coated ferrite, or a rare earth disk the size of a coin. It has no power source. Nothing is being spent to keep it working. It has been holding a shopping list to a metal door for years, and it will keep doing so for decades. Hold it a centimeter above a steel paperclip lying on the counter, and watch the paperclip jump. Now consider what just happened. Beneath that paperclip is the entire Earth. 6,000 billion tons of iron and rock and water, every atom of it pulling downward on that scrap of steel, continuously, with the full and undivided strength of planetary gravity. That pull is the reason you cannot jump more than a meter off the ground. It is the reason the atmosphere stays. It holds the oceans in their basins, and the moon in its orbit. And a few grams of iron in your fingers beat it without effort. Not narrowly. There is no contest, no moment where the paperclip hesitates between the planet and the magnet. The planet was never a serious competitor. The electromagnetic force between two protons exceeds the gravitational force between them by something on the order of 10 to the 36th, which is why an object you could swallow can overrule a world. Nobody knows why that ratio has the value it has. I want to be clear about what kind of ignorance this is, because it is not the ordinary kind. This is not a quantity we have failed to measure precisely. We have measured it fine. It is not a quantity that is hard to define. It is perfectly well defined. It is a number that appears in nature, that no accepted theory derives, that no principle explains. and that seems arbitrary in a discipline whose entire premise is that nothing fundamental is arbitrary. It has a name, the hierarchy problem, and the name is a piece of politeness. Naming something does not explain it. The extra dimensions we discussed earlier were one attempt to dissolve it, by proposing that gravity is not weak at all, but merely diluted across directions we cannot access. Other attempts exist. None has been confirmed. So we arrive at the end of the case against ourselves, and I want to lay it out plainly before we turn the corner. We cannot agree on gravity's strength on a bench. We cannot test its law below the width of a hair or above the size of a galaxy without it failing or needing help. We cannot explain why it is 36 orders of magnitude weaker than everything else. We cannot say what it is. We cannot quantize it. We cannot quantize it. That is a fairly complete inventory of failure for the first force anybody ever wrote down, which makes what I am about to show you next very difficult to explain, because in the middle of all this, physics also performed the single most precise measurement of anything, ever, and what it measured was gravity. Part 14. 1/1000th of a proton. On the 14th of September 2015, at just before 5 in the morning Central European Time, two machines, 4,500 kilometers apart, twitched 7 milliseconds apart. Let me take you inside one of them. The detector is an L, with each arm 4 kilometers long. Down each arm runs a steel tube more than a meter wide, pumped down to one of the largest and emptiest artificial vacuums on Earth, because a stray air molecule drifting across the beam would ruin everything. A laser is split at the corner and sent down both arms at once. At the far end of each, a mirror weighing 40 kilograms hangs from a cascade of pendulums designed to isolate it from the ground, because the ground is never still. The light bounces back and forth hundreds of times, then returns to the corner, and the two beams are recombined so that, in the ordinary case, they cancel each other out perfectly, and the detector sits in darkness. That darkness is the measurement. Any change in the relative length of the two arms lets light through. At that moment in September, a signal swept up through the detector's sensitive band, rising in frequency and amplitude over about 0.2 of a second, and stopped. The same pattern appeared at the second detector in the other American state 7 milliseconds later, which is about how long it takes something traveling at the speed of light to cross the distance between them. What had arrived was a gravitational wave. 1.3 billion years earlier, two black holes of roughly 36 and 29 times the mass of the Sun had spiraled into each other and merged, converting about 3 solar masses of material into pure gravitational radiation in a fraction of a second. For that instant, the collision radiated more power than all the light of every star in the observable universe combined. Then the ripple spread outward for 1.3 billion years, thinning as it went, until it reached a planet where, in the meantime, life had arisen and worked out what to build. The stretch it produced in those 4-kilometer arms was about 1 part in 10 to the 21st. In physical terms, the length of each arm changed by a distance thousands of times smaller than the width of a single proton. We built something that could feel that, and we did not merely detect it. From the shape of the signal, we read off the masses of both black holes, the distance to them, and the spin of what they became. Now hold that beside the other thing. In a quiet laboratory, in a stable room, with two spheres of metal sitting on a bench about 10 centimeters apart, we cannot agree on how hard they pull on each other to better than a few hundred parts in a million. Those two facts are true at the same time, on the same planet, in the same decade, often in the same institutions. We can hear two black holes collide across 1.3 billion light-years by measuring a change in length smaller than a proton, and we cannot settle an argument about two lead balls on a table. And it is not only the waves. The microscope satellite spent 2.5 years in orbit doing one thing: watching two test masses, one titanium alloy and one platinum alloy, fall around the Earth together, checking whether different materials fall at different rates. Its final result, published in 2022, found no difference at the level of a few parts in 10 to the 15th. Galileo's proposition that all things fall alike has now been confirmed to a precision of 1 part in 1,000 million. And lunar laser ranging, as we saw, shows that the strength of gravity is not drifting over time to better than 1 part in 10 trillion per year. So here is the shape of it, and this is the answer to the question we started with. We can measure that gravity is not changing, superbly. We can measure that all things fall alike, superbly. We can measure the ripples gravity makes across 1 billion light-years, superbly. What we cannot measure is gravity itself. Every triumph on that list is a measurement of a relationship, a comparison, a ratio, a difference. Every failure is an attempt to get at the thing on its own, in units, as a quantity, which means the precision never failed. That is the turn. I think most people, reaching the end of a story like this, would conclude that our instruments are not good enough yet, and that one day a better machine will come along and close the gap. That is the natural reading, and it is the wrong one. Look at the record again. The instruments have been improving continuously for 228 years, and the disagreement has grown alongside them. In 1998, the official uncertainty was multiplied by 12, and it was multiplied by 12 precisely because the new measurements were better. In 2018, the two finest determinations ever made contradicted each other, and they could only contradict each other because they were so sharp. Blurry results agree. It takes precision to disagree properly. The number gets sharper, and the disagreement gets wider. That sentence has been sitting in this video since the 5th part, and I want to now say what it actually means, because it is not a description of a problem, it is a definition. Precision is not a way of getting closer to an answer. Precision is a way of finding out whether you understand something. When you understand a thing, sharpening your instruments produces convergence, because everyone's errors are shrinking toward a shared truth. When you do not understand a thing, sharpening your instruments produces divergence, because each experiment's hidden assumptions become visible as its random noise falls away, and hidden assumptions do not agree with each other. The disagreement was never noise obscuring the answer. The disagreement is the answer. It is the sound of a description being pushed past the edge of its own explanation, and gravity is the place where physics has pushed hardest and found the edge closest. Which brings back a phrase from earlier tonight. General relativity is a theory that tells you what, and refuses to tell you why. I offered that as a criticism of one theory. It is not. It is the description of our entire relationship with this force, and it has been from the beginning. Newton told us what gravity does, and said openly that he would not pretend to know why. Einstein told us what gravity does, in far greater detail, and also declined. Every measurement since has been another statement of what, made more precisely, with the why untouched underneath. 228 years ago, a man sat outside a shed in South London, with his eye at a hole in the wall, watching a rod turn through an angle he could barely see, and people said he had weighed the world. We are still weighing the world. The shed has become a chamber under a hill in Wuhan and a 4-kilometer vacuum tube in the Louisiana pine forest. The lead spheres are still lead spheres, and the answer is still not settled, not because we have been careless, but because we have been so careful that our carefulness has started reporting back on us. That is why, the more precisely we measure gravity, the less we understand it. Not because the measurements are failing, because they are working exactly as designed, and what they are measuring is the size of the gap between what we can describe and what we can explain. Every time we sharpen the instrument, we see the gap more clearly. You will feel it in a few hours, when you stand up. Something will hold you to the floor, as it has every second of your life, with a strength nobody on this planet can state to more than 5 digits, by a mechanism nobody can name, obeying a law nobody has tested across most of the distances it claims to cover. It has never once let you go, and it has never once explained itself.